So first of all, thank you so much for having me. And I really, really regret not being able to see everybody physically. I hope that this will be possible soon. And during the talk, please feel free to interrupt me with questions. One of the things that I'm going to mention in this talk is that interaction actually can help make communication more efficient. So please do interact if you feel like it. So what I wanted to tell you about today is recent work with my student Aviv and with Gilat Kol from Princeton about distributed zero-knowledge proofs. So I wanted to start by telling you a little bit about proofs in theoretical computer science in general, and then we'll talk a little bit about distributed proofs and proof labeling schemes. And then we'll introduce this concept of zero-knowledge proofs, and that will be pretty much the background. And then we'll talk about distributed zero-knowledge proofs. We'll see how they can be defined. I'll give one concrete example for three coloring, and if time allows, I'll also show you a generic construction that is able to take any proof labeling scheme and construct out of it a zero-knowledge proof. So let me start with what is a proof in general when we are talking about proofs in computer science. So we all know what proofs are in math, right? A proof is something that you write down on a piece of paper, or possibly many pieces of paper. And after you've written the proof, you go away. And the proof it contains everything that is needed to verify the truth, the validity of the statement that you were trying to prove. But in computer science, many times when we talk about proofs, we are actually thinking about a more interactive process, where instead of just writing down the proof and going away, we actually are able to interact with the prover. We can ask questions and the prover then has to answer them. And as you know, this can actually really help in class. You can ask, wait, I didn't understand this point, or I don't believe that this point is true. Can you convince me? So this is what's called an interactive proof. It was introduced by GOLDWASSER and MICALI and Mike SIPSER. The formal definition is that we have two entities, a verifier and a prover. The verifier would like to become convinced that some instance X belongs to a language L. For example, X is a graph, and L is the language of all three colorable graphs. And the verifier is computationally bounded, so it can't actually verify this by itself. It's too difficult. So it's going to enlist the help of a prover, which is unbounded computationally. And then it's going to be able to talk with the prover interactively back and forth. And the prover will try its damnedest to convince the verifier that the answer is yes. And after they have this interaction, the verifier will decide, am I convinced, in which case I accept, or am I not convinced, in which case I reject. And in order for this to actually be efficient, we're going to need the verifier to be randomized. So you see here that the verifier is going to be able to toss some coins to determine what it should say to the prover. So let me move the slide. Sorry, I'm having a bit of a tough. Okay. What do we want this interactive proof to satisfy? The two classical conditions are completeness and soundness. Completeness means that every instance that is in the language, there is a prover that can make the verifier accept with high probability. And I wrote here that the acceptance probability is 2/3, but it actually doesn't matter that much what threshold you choose, because you can just repeat the conversation a few more times and you can amplify the completeness pretty much as high as you want it, as long as it's, polynomially bounded away from you. The other criterion is soundness. If the instance is not in the language, then nobody should be able to convince me that it is in the language. So for all provers, when I interact with the prover, the probability that I actually become convinced is at most 1/3. And again, 1/3 is somewhat arbitrary here as a threshold. So these are interactive proofs. Interactive proofs are actually extremely powerful. So what do we know in classical complexity theory? If you look at the class P of problems that we know how to solve efficiently in polynomial time. Adding a prover lifts us up to the class NP, where there is some witness, which we don't necessarily know how to find it, but if you give it to us, we will be able to efficiently verify that we should accept that really this instance isn't the language. And this is with no interaction and with no randomness. If you add interaction, you go all the way up to the class P-space. A really famous and celebrated result by Shamir shows that the class interactive proofs, IP, of languages that can be recognized by an interactive proof is equal to P-space, the language, the family of languages that can be recognized by a Turing machine that uses polynomial space, but not necessarily polynomial time. So for example, SAT, satisfiability, is in P-space. Let me take a look quickly at the chat. Okay. All right, so this is the power of interactive proofs in classical complexity theory. Let's talk a little bit about proofs in distributed computing. So here, the typical setup is that we would like to determine if the network has some property which is desirable. For example, maybe we computed a spanning tree for the network, so we're storing the state of the nodes, the spanning tree itself. But we're worried that maybe the network has changed. Maybe some links have failed or some links were added or some nodes have joined. We'd like to be able to verify that what we previously computed is still true. So for this purpose, we are going to ask Prover to assign labels to the individual nodes of the network. And then the nodes will locally look at their own label and their neighbors' labels and decide if they accept or reject. In other words, if they became convinced that the network has the property P, or if they're not convinced. So this notion was formally introduced by Amos KORMAN and KUTTEN and Aviv PELEG, but it was actually present already, not explicitly, but it was implicit in prior work on self-stabilization. So let me give you a bit of a formal definition here, and the red asterisk here on top is because the model that I'm going to present is not exactly the model that was originally presented in the paper, but it's very close. So we're going to assume that we have a network of nodes and a set V of nodes. Every node initially has a unique identifier, and it knows its own identifier and also its neighbors' identifiers. It may have some input, for example, who is the parent in the spanning tree that we'd like to verify, or maybe it doesn't have any input and we just want to check some property of the communication graph. And the way that the proof system works is that the prover assigns to every node a label, which is just a binary string of some length L. And then every node sees its own label and the labels of all of its neighbors and its inputs if it has an input, and it's going to decide accept or reject. And we say that this configuration, the network plus the inputs, is accepted if everybody accepts. It's enough for one node to reject, to sort of raise a red flag and say, I'm not happy, in order for us to say that it's rejected. And the cost of the scheme is what we would like to minimize. The length of these certificates, these labels, is what we would like to make as small as possible. And interestingly, you can even gain useful information from labels of only 1 bit. For example, if you would like to check that the network graph is bipartite, you can tell every graph which side it's on, just 0 or 1. So the label is 1 bit. And then you just check, do all of my neighbors have the opposite label from me? If they do, I accept, otherwise I reject. And actually it turns out that, so we just said that 1 bit is sometimes useful. In a quadratic amount of bits, you can do anything. Any graph language can be decided by just asking the prover to give the entire network graph G to every node in the network. And of course, we don't necessarily trust that the prover really told us the true graph, because the prover always wants to make us accept. So we need to check. And checking just means here that when the prover gave you the graph, you need to make sure that, first of all of the neighbors that you see actually match with what the prover claimed are your neighbors in G. And the other requirement is that we all got the same graph. So we need to compare what the prover told us and what the prover told our neighbors, just to make sure that it's the same. And once you've done this, then you know that G really is the network graph, and you can locally compute whatever you want. You can check if the graph is three-colorable, any property that you want, because we're not interested in computational hardness here, only in the length of the certificate. And this basic model has been extended in many ways. Proof labeling schemes have been taken in many different directions. For example, you can ask what happens if instead of only talking to your neighbors, you get to talk to some radius further away from you. Or you can give more information. For example, what if you get to see the inputs of other nodes, not just your own? What if you are allowed to send different messages to different neighbors and so on? Many have looked at these variations. It's really interesting to ask what happens if you add randomness. Instead of just sending whatever label the prover gave you, maybe you want to flip some random coins and send random messages to your neighbors, or maybe you want to send random messages to the prover, who knows, right? So this has also been looked at in all sorts of interesting directions. For example, certifying approximately that the property holds, or being sensitive to how far we are from the property holding, and so on. But kind of interestingly, all of this theory of distributed proofs has been developing, it looks like almost independently from the general through line of proofs in computer science. It looks like there hasn't been a lot of cross flow between these two areas. And I think one thing that's really interesting to ask is, what can we take away from this really beautiful and rich theory of proofs in theoretical computer science? And vice versa, what can they take away from our notion of proofs in distributed computing? So let me give you just a few examples of ideas that we can take from theory of computer science and use them for distributed proofs. One thing that we said is useful is interacting with the prover. And it turns out that in the distributed setting, if you allow even one round of interaction, just sending something to the prover and getting an answer, that can already help in some cases reduce the size of the label exponentially. And if you allow more rounds, for example, 3 rounds or more, in some cases you can bring the labels down to a constant. So interaction can be very helpful. Here is another concept from theoretical computer science: probabilistically checkable proofs, PCPs. A PCP is a special type of proof where the prover is going to write down the proof, and the proof might be very long, but the verifier is only allowed to access a constant number of locations in the proof. So this is really surprising that you can even do this. But again, you write down this huge proof, the verifier is going to choose a small number of locations in the proof and only read those bits. Based on these queries, it needs to decide, do I accept this proof or do I reject it? And some of the most famous work in complexity theory has shown that this is actually feasible for all languages in NP. You can write down a PCP of polynomial length where the verifier only reads a constant number of locations. So then we wanted to ask, can we do the same in a proof labeling scheme? Remember this universal proof labeling scheme that I just described, where the prover gives every node the entire graph. So this is quite long. This is n squared bits because the prover has to write down the entire graph. Can we actually get to a situation where the prover writes down this very long proof, but all the nodes in the network only read a constant number of bits and only send a constant number of bits? And it turns out that the answer is yes, you can actually do this. This is ongoing work. We're not quite done with it yet, but yes, you can import these ideas from PCPs and you can get efficient distributed PCPs. And finally, what I really wanted to devote the talk today to is zero knowledge proofs. This is a very cool type of proof, which again, we've been looking at, can we get these really nice properties in distributed proofs as well? And it turns out that the answer is yes. So before I move on to talking about zero knowledge proofs, this is a really good point for questions if there are any. Okay, so let me tell you a little bit about zero knowledge proofs. The slide is not moving. Here we go. Okay, one thing that I wanted to mention is often when you look at these things, there is a bit of a mismatch between the complexity theory perspective and the distributed computing perspective. Because complexity theory, usually everything is computationally bounded. The verifier is computationally bounded. Sometimes we even want the prover to be computationally bounded. And in distributed computing, we usually don't care about local computation. We only care about communication, the length of the labels, how many bits I need to send to my neighbors, and locality, how far I need to communicate in the network. So because of this, you sometimes get really interesting questions which really force you to take a new kind of perspective and a new look at these classical ideas and put an interesting twist. Okay, so let's talk about zero knowledge proofs. This is a special kind of interactive proof where, in addition to the properties that we wanted before, which are completeness and soundness, now we're also going to demand that the verifier should not learn anything from the prover when they talk, except for the fact that the instance X really is in the language L. So the verifier should become convinced that it should accept, but except for that, it should learn nothing. And in my opinion, this is a kind of magical thing which seems like it should not be possible. Think about proofs that you've seen for mathematical claims. You have to prove lemmas. You have to learn many properties of the object you're looking at. You have to expand way beyond just the fact that the answer is, yes, this theorem is true. But it turns out that zero knowledge proofs are actually possible. And I'm going to show you one example, which is SUDOKU. So SUDOKU is a game. I'm sure all of you know it, but just in case, let me explain how it works. You get, it's a type of puzzle where you get a 9x9 board, and some of the squares are already filled in with numbers. And your goal is to fill in all the rest of the squares with numbers as well, in such a way that for every row and for every column and for every square, every number appears exactly once. So for example, if you look at this square here, you see the numbers 1 through 9, each number appearing exactly once. And the same for each column and for each row of the SUDOKU. I know because I worked quite hard to solve it. So this is the SUDOKU puzzle. Now let's say that I would like to convince you that I know a solution to a specific puzzle. I want to show off, but maybe there's a reward. So maybe I don't want to tell you the solution. I don't want you to learn anything about the solution other than the fact that I have it. So let's see a zero knowledge proof for the solvability or having a solution to a SUDOKU puzzle. So I'm going to use a 4x4 puzzle just to make life easier. And I'm going to present this proof as a physical thing using cards, but actually everything that I'm going to say here now can be implemented using cryptography, using encryption. So for now, the physical solution is following. I'm going to use cards with numbers. Since it's a 4x4 grid, I'll use numbers from 1 to 4. And the cards will have two sides. On one side, I'm going to write the numbers in my solution. And the other side, you can't see the number, okay? It has some other drawing or whatever. So I, as the prover, will write the solution on these cards. And then I'm going to put the solution on the board, but I'll put the cards face down. So you can't actually see my solution. I wrote down the solution, but you can't see it. You only see the back of the cards. And now, why should you believe me that this is the correct solution? You can't actually see the solution. I'd like to convince you that it's a good solution, that it's proper, but I don't want to tell you anything about the solution. So how can we do that? So here's the really cool idea. You, as the verifier, will choose a random constraint, a random row or a random column or a random square. And then you'll ask me to convince you that the solution respects that constraint. So let's say you picked this particular square here and you ask me to convince you that this square contains all the numbers from 1 to 4. I'll take the cards that I laid down in the square and I'll shuffle them without showing you what the numbers were. And then after I shuffle the cards, I'm going to reveal the numbers. And now you will see that the square really did contain in my solution the numbers 1 through 4. The number 1 was already fixed in a particular location. And the solution that I wrote down had the numbers 2, 3, and 4. So at least this square, my solution respects the constraint. And of course, this is only one constraint out of many, but if you're still not satisfied, you can ask me to put down the cards back face down on the board and pick a different constraint. And you can do this as many times as you want until you are as convinced as you would like to be. And now, what did you learn from this interaction with me? You became convinced that I have a good solution. But did you learn anything from this interaction? When I revealed the cards to you, you saw what you would have already known if only you believed that my solution was good, right? If a solution is good, it means that for any constraint, you will see the numbers 1, 2, 3, 4. And this is what you saw. You didn't learn the order that they were laid down. Well, because of that, this proof is actually zero knowledge. You learned nothing other than the fact that I do have a correct solution. Any questions about this example?
Who takes care of shuffling?
Yeah, it's a great question. So I'm describing this as a physical thing, right? We have these cards, we put down the cards, and then the prover picks up the cards, shuffles them, and reveals the numbers, right? So I pick up only the constraint that you chose. If you chose this particular square, then I'm going to take only the cards from that square. And then I'm going to shuffle them so the order becomes, completely lost. And then I will show you that the numbers there were 2, 3, 4.
But then how are we sure that the prover did not do some replacing of cards with some other cards?
So in this physical pretend process that I'm describing, you see that the prover is taking the cards from the board and actually shuffling them, right? So there is no pinky business going on because you see that the physical cards are still there and they're not being replaced. And it's a great question, how can you implement this with cryptography? So for that, they use something called a binding commitment, which is a way to sort of like implement this putting the card face down idea. You can encrypt the number in such a way that it's binding. Afterwards, you can give me the key that will open the encryption, but there's only one proper key. You cannot lie to me and say, oh, here's a different key which will reveal a different number. There's only one way to open the encryption. So essentially, this is committing to a specific number that is written down in that particular square. And the shuffling operation needs to happen under the cryptography, right? So this is non-trivial.
Thanks.
Any further questions?
Yes, I have one quick question. How is the verifier in all of this? And also the things you said before quantified, like who decides what the verifier is allowed to do?
Okay, so let's look at the formal definitions and then ask me again, okay? Because this is what's called an excellent question. I do have a slide prepared for it. So how do we formally capture these notions that hopefully we've understood intuitively? So we wanted to formalize this idea that the verifier shouldn't learn anything from the prover except the fact that this particular instance is in the language. So first of all, what does it mean to learn something from the prover? And then it also turns out that we need to carefully think about what nothing means. What does it mean to learn nothing? And the definitions, after some evolution and many different variations, it turns out that the right way to think about this is through something called a simulator. So I'm going to say that the verifier learned nothing from the prover. If the verifier can basically generate the same conversation that it would have with the prover by itself. So if only you knew that this instance was in the language, you could have generated the entire conversation that you would have had with the prover without the prover even being there. So think about the Sudoku example. If only you believed me that the solution was correct, you could have simulated everything else in your own head. You could have, pretended that you're seeing the cards being shuffled and then that the numbers being revealed were 1, 2, 3, 4. You didn't need any extra information in order to carry out this simulation. So this is one really important aspect of the definition. And the second aspect is learning nothing. So here the question is, what does it mean to generate the same conversation that I would have with the prover? You can define this in several different ways, but ideally I would like this conversation that I'm pretending to have in my head to be very close to the conversation that I would have had with the prover. So more formally, a zero knowledge proof system for some language L consists of a verifier V, which in complexity theory is a polynomial Turing machine, a prover P, which is unbounded computationally, and a simulator S, which is again polynomially bounded. It's a Turing machine, which is polynomial. And I would like this to be complete and sound. So for every instance that's in the language, the prover should with high probability convince the verifier to accept. And for every instance that is not in the language, the prover should with high probability not be able to convince the verifier to accept. And the zero knowledge property means that there is this simulator which can generate this pretend conversation. So it can essentially generate the same interaction that the verifier would have with the prover. And there's several different ways to capture the same, as I said. In information theoretic zero knowledge, I want the simulator to generate a transcript, a conversation transcript, which is from exactly the same distribution as the conversations that the verifier would have with the prover. This is information theoretic. There's no difference between the conversation that I would really have with a prover P and this pretend conversation that the simulator generates. So this is a very strong definition. A slightly weaker definition is called statistical zero knowledge. Here, the simulator outputs a conversation which is from a distribution that might not be exactly the right one, but it's very close. The difference between them is some negligible function. It's smaller than 1 over any polynomial. And finally, computational zero knowledge, which is the weakest definition here, requires that, okay, the simulator might not be doing its job very well, but no efficient algorithm can tell. So any polynomial Turing machine, if you give it a transcript that is this fake transcript generated by the simulator, or if you gave it the true conversation with the prover, it wouldn't be able to tell them apart except with some negligible probability. So essentially it can only guess, is it really the prover that I generated this conversation with, or the simulator that was only pretending to have a conversation with the prover? So these are the 3 classical types of zero knowledge proofs. And what do we know about them also? Before that, just some important observations about the definition. First of all, this is a class of zero knowledge, which is called zero knowledge against honest verifiers. The verifier here is not really trying to extract information from the prover in a malicious way. It's going to interact with the prover in some honest way, just trying to become convinced that it should accept the instance. But then it's going to look at the conversation and say, what can I learn from this about the instance? Okay, so it's not malicious, it's only curious. There is also zero knowledge against malicious verifiers, which actually try to squeeze out information from the prover by not following the correct algorithm. Next, we are not trying to protect cheating provers. So when the instance is not in the language, the approver is actually, if it tries to convince me to accept, it's not being honest, it's cheating. And in that case, it's fine to extract as much information as you want. And you can see this from the definition. If you look at the definition of zero knowledge, the simulator only needs to work when X is in the language. For instances that are not in the language, maybe you can't simulate the conversation. And finally, and this is really important, actually the verifier can still learn stuff about this input X, because the verifier is a polynomial Turing machine. It can compute things about X, right? Maybe not determine if it's in L or not, but it can still do some computation and learn things that it didn't know initially. So zero knowledge really only protects the prover. The verifier can figure stuff out, but only stuff that it can compute by itself. It can't learn anything from the prover that it was not able to compute alone. So this is the formal definition of zero knowledge. And now, Yannick, did this answer the question?
Yes, thanks.
Great. Any other questions about zero knowledge? Okay, so let me tell you really quickly what we know in complexity theory about various types of zero knowledge. So first of all, this amazing result by GOLDWASSER and MICALI and Vigdusson showed that for the entire class NP, we can get computational zero knowledge. We do need a cryptographic assumption for this. We need to assume that one-way functions exist. And this is so that we can implement these binding commitments. And actually, if you think back to this SUDOKU example, SUDOKU is NP hard. It's NP complete if instead of a 9x9 board, you allow the board to be n by n for any n. So you can take this proof that I showed you, and you can implement it using cryptography, using one-way functions. And from that, you get computational zero knowledge for the entire class NP. What about statistical zero knowledge? Turns out that it's actually quite limited. It's only languages that are in two complexity classes called AM and co-AM, basically only one interaction with the prover in an interactive proof. So this is not believed to be all of NP by any means. It's believed to be pretty restricted. And for the strongest definition for information theoretic zero knowledge, we have very few examples. Not many languages are known to be in this class. And beside these notions that I defined here, there are many, many variations. And you can ask, for example, like I said, what if the prover needs to be efficient? What if I would like the proof to be almost linear in the length of the instance X? You can impose many additional requirements, and these have been studied. And recently, actually, they have started having fascinating applications in cryptocurrency, in how you can have a blockchain which is encrypted in order to actually have anonymity. Because if you look at Bitcoin, Bitcoin is not anonymous. Everything is out there for everybody to see. The only thing that is anonymous in Bitcoin is that you don't know which wallet belongs to whom. So it's like a phone number. I don't know whose phone number this is, but I can see which phone number has been calling which other phone numbers. So if you want to avoid that, if you want to get true anonymity, you're going to need to use more crypto, and then zero knowledge proofs are incredibly useful. Okay, so let's talk now about distributed zero knowledge. So we'd like to combine these two notions to take proof labeling schemes and require now that the nodes of the network shouldn't learn anything from the prover when they interact with it in order to decide if they should accept or reject the network graph. So for example, suppose you have some trusted overlay network like a cellular network, but the phones are also talking to each other directly in a mesh peer-to-peer network. And you want to do some sensitive computation, like let's say coronavirus contact tracing. So this is pretty sensitive, right? I do trust the cellular network to carry out this computation, but I wouldn't want to learn as an individual node in this network too much about other users in the network. I would like to protect their privacy. This is what we're going to be able to capture with this definition of distributed zero knowledge. So the first thing we have to do is to ask ourselves, okay, what does zero knowledge mean when we translate it to a distributed network? We said that zero knowledge should mean that the verifier doesn't learn anything from the prover. So in our case, who is the verifier? It's the network. It's a network of verifiers. And we don't have any computational assumptions. So before, the prover was able to compute really hard things, and we wanted to protect its ability to do that. But here, the nodes can do anything they want computationally. So this is not something that we need to protect the prover. On the other hand, the nodes have a very local view of the network, and the prover's advantage is that it sees the entire network. This is what we need to protect. So in distributed zero knowledge, it's more about privacy than it is about computational hardness. We're trying to protect the global view of the network that the prover has when it chooses the labels in such a way that the nodes can still become convinced that they should accept, but they shouldn't learn too much about the network that they are running in. This is kind of the natural translation of the concept of zero knowledge to distributed networks. So let me be a little bit more formal now. I would like to define a proof system in a way that is kind of equivalent to an interactive proof, and then impose this requirement for zero knowledge on top of it. So a distributed proof system, I'm going to parameterize it in order to be as general as possible by some class of distributed algorithms. So as I mentioned before, there's a lot of research on what happens when you let the verifiers do various things, if they can be randomized, if they can communicate to some distance, if they can send different messages to different neighbors. So pick some class A of distributed algorithms. This will be the type of verifier that we're going to use. Okay, for example, maybe my favorite class is congest algorithms that send log n bits in every message and they communicate for 3 rounds. That will be the class from which the verifier algorithm will be drawn. And parameterized by this class, a proof system is a pair of a verifier. The verifier is an algorithm from the class that I fixed. And the prover is completely unbounded in every way. It sees the entire network. If there's input, it sees the input as well. And it's going to try to convince me that my input is in the language L. So how does this system execute? First of all, the nodes are going to talk back and forth with the prover for some number of rounds. And in this part of the proof, I'm going to assume that they have private randomness for every edge. So basically, you can think of it as when we start out, every node sends a random string to every neighbor, which the prover cannot see. This is really important. So the prover can't see the randomness of the nodes. So we talk back and forth for as many rounds as we want. Then we run the verification algorithm, which is going to tell us, should we accept or reject? Okay, so all of this interaction and talking to our neighbors, this generates a view where we can record everything we sent to the prover, everything the prover sent back to us, and then everything we sent to our neighbors and what they sent to us. And out of that, you're going to decide what to do. Are you convinced or are you not convinced?
Rotem, can I ask a quick question?
Of course.
So the language L here is the topology of the network, or do we also have inputs?
It can be either a graph language, so just a family of graphs, or it can be a set of configurations, like a graph and an input. For example, let's say that I would like to verify a spanning tree. Then L will be a language of pairs, where the first element is the network graph G, and the second is an assignment telling every node in the network, this is your parent in the tree. Okay, so for simplicity, I'm really ignoring this aspect of the input, but it is there. It can be part of the input as well. Does that answer the question, Kelly?
Yeah, thanks. Yeah.
Okay, so this is how the proof system works. And as usual, we want this to be sound and complete. So if my input is in the language L, then the prover should with high probability cause all the nodes to accept. But if the input is not in L, then some node should reject with high probability. And now let's talk about zero knowledge. What is distributed zero knowledge? So remember we said that in zero knowledge, the verifier can learn stuff about the input. Whatever it is able to compute by itself, it can, learn. The same property is going to occur here. The verifier is a distributed algorithm. A distributed algorithm can learn stuff about the network that it's executing in. What we're going to demand is that that's all. Beyond what an algorithm from the class A can learn, our verifier should not learn anything. So we're going to capture this formally, again, by the existence of a simulator. A simulator is going to be some distributed algorithm from the class A, and it's going to execute in the network and output at every node a fake view, kind of pretending that the prover was there and trying to say, this is the view that you would see. This is what you would send to the prover. This is what the prover would send back. And then you would talk to your neighbors. They would say this, you would say that, and so on. Basically, a view is output at every network. And zero knowledge means that this view should be correct. You shouldn't be able to tell if it's the prover that you interacted with to generate this view, or if it was the simulator that was generating the view across the entire network. So a bit more formally, if you give me a proof system, this proof system induces a distribution over views because everything here is typically randomized. I do want to allow the verifier to be randomized. And actually the prover will also be randomized. So you get this view, which we denoted by pi of VG, the view of node V in the graph G. If there's an input, you need to add the input here as well. And this is a random variable, which is just a list of the randomness of the node and everything it's ever sent or received. And we are going to require that there is a simulator which outputs this fake distribution of views. This is the joint distribution of all the views of all the nodes in the network. And it should be equal to the true distribution of views that would be generated when you interact with the prover. So this is the definition of zero knowledge when you think about giving the verifier the ability to compute things using its own powers. But you can actually, since we're in the distributed world, you can actually have a stronger requirement. What if I want every node to be perfectly protected? I want nodes not to learn anything about anybody else in the network. You can ask for that as well, and we call that strong distributed zero knowledge. So here, instead of having a simulator, which is a distributed algorithm, so you can learn stuff, but only what an efficient distributed algorithm can learn, here we're going to demand that actually you learn nothing about anybody. So the simulator here will just be a local function. It takes your own input, your neighbors and your input if you have it, and it outputs a view. It talks to nobody. There is no prover, and it doesn't talk to any neighbors or anybody else in the network. It's just a local function which takes your own view and generates this fake conversation. And again, we require that this should be the correct distribution. So the distribution of this view output by the local simulator should be exactly the same as if the prover was there and I was talking to the prover and to my neighbors. So these are the two types of distributed zero knowledge. One is weaker because the simulator is a distributed algorithm. You can learn stuff about the network, but only whatever an efficient distributed algorithm can extract. So it's still local information that you're learning. The second type is even stronger. You're not going to learn anything about the network beyond your own initial view, which is your neighbors and your input. So let me show you an example because I think these definitions are a bit of a mouthful and I think a definition will help a lot. So the example I wanted to show you is 3 colorability. Is the network 3 colorable or not? And this is a really famous example of a proof labeling scheme because it's so nice and simple. I can just ask the prover to give every node V a label, which is the color of V in a proper coloring. And then how do you verify this? You just send your color to all your neighbors and you make sure that they got a different color from you. Okay, so in terms of cost, this costs a constant number of bits per node, which is really nice. But is this zero knowledge? So when the prover gives me the colors, and then I compare colors with my neighbors, is this zero knowledge? By comparing colors with my neighbors, do I learn something non-trivial about the network? Turns out that the answer is yes. Actually, you do learn something non-trivial about the network. So here's an example of two graphs, which are not the same graph. And the bottom node here, node 0, can learn whether or not there's an edge between its two neighbors here by just looking at whether they have the same color or not. In this left graph, the two neighbors of the bottom node must receive different colors because there's an edge between them. In the rightmost graph, the two neighbors of the bottom 0 here need to get the same color. So if node 0 really just looks at the colors of its neighbors in order to check whether the coloring is proper, then you've learned stuff about the network that you were not supposed to learn. You have two neighbors, you're not supposed to learn whether they have an edge between them or not, but you are able to extract this information. So we'd like to avoid that. We'd like to somehow design a mechanism where nodes can verify that they did get a proper coloring, but without learning the colors of their neighbors. So here's how you can do that. Here's a zero knowledge proof for 3 color nodes. I'm still going to ask the prover to give the nodes a proper coloring. But before giving the colors, the prover will randomly shuffle them. Just pick a random permutation on 1, 2, 3 and just shuffle the colors at random. Then it's going to give every node the randomly shuffled color. And why am I doing this? It's to make sure that the view of every node, what you receive from the prover to start with, is just a uniformly random color from 1 to 3. Okay? This by itself gives you no information. And now how are you going to verify that your neighbors got different color without actually showing them the color that you got? Now here's a way that you can do that. And this is heavily inspired by the amazing zero knowledge proof for graph non-isomorphism. So you're gonna basically try to trick the prover into revealing whether it gave you the same color or not. So suppose that we have these two nodes U and V, and they have these colors CU and CV. They want to determine if it's the same color or not. So they're gonna toss this random coin, which is private. The prover cannot see this coin. In one case, they're going to choose the same random color, A, and both of them will send A to the prover. Okay, so in this case, the prover gets the same color from U and from V. In the other case, they're just going to choose a random permutation, and they're going to each apply the permutation to their own color, and they're going to send the prover the randomly permuted color. And now what are we going to ask? The prover should tell us what the value of the coin was. So if the colors were different, then whatever permutation you apply to them, they will still be different, right? So the prover will always know that we decided on the right path, where you just apply a random permutation. It's going to get different colors, and it's going to know that this is what we decided. But if it was the same color, then these two options look the same. In both cases, the prover just gets a random color, which is the same for both U and V. So it can't actually tell them apart, it can only guess. And it has probability 1/2 of getting it wrong. So the soundness here is only 1/2, but you can repeat it in order to amplify the soundness and get it to be low. So just to summarize what we're doing here, for every edge, we're going to need to pick this random coin and then either agree on a random color and both send it to the prover, or agree on a random permutation and then both apply it and send their permuted color to the prover. So all in all, every node needs to send a number of colors, which is its degree. So for every edge, it's doing something different. And then the prover is going to have to respond by saying, for this edge, you picked a coin of 0. For this edge, you picked a coin of 1, and so on. So also the communication coming back will be the degree of U. And the nice thing here is that the total communication of the entire network with the prover is only the number of edges. It's order of the number of edges in the graph. We conjecture that this is optimal. It's hard to imagine that you can do any better. But there is some overhead here because when we weren't asking for zero knowledge, we could do it with total communication, which is only the number of nodes. So we're working now on trying to figure out, is this optimal or not? And in terms of zero knowledge, let me describe the simulator, which basically knows nothing and is able to locally generate a conversation that looks the same as the conversation with the prover. What do you need to do? Well, the prover gives you a color which looks just random. So the simulator will just pretend it's receiving this random color from the prover. After that, it's going to simulate what happens for every edge. And what is it that happens for every edge? We pick this random coin, and then we pick either a random color or a random permutation. We send the appropriate thing to the prover. And what do we get back from the prover? If the prover is honest, it knows what the value of the coin was, and it's going to respond with the correct value of the coin. This should be B here, which is the coin, not the color A. Okay, but again, the prover always gets it right. The honest prover always gets it right. So I know what it's going to say. It's going to give me back the correct value of the coin. This is the simulator. I didn't need to know the colors of my neighbor. I didn't need anything beyond just knowing who my neighbors are. So this is strong zero knowledge. And again, there is some overhead here in order to achieve. Any questions about this proof system? Okay. What else can we do? What other kinds of zero knowledge distributed proofs can we design? So one option here is to basically have a generic construction which uses ideas and tools from cryptography, and it can do whatever you want, but it might be super expensive. So you can use something called secure multi-party computation. This means that you have K or N in this drawing parties. They each have an input and they want to compute some joint function F of their inputs, but they want to do it securely. So they would like to learn nothing about the values of the other inputs, except for their own, the own input X and the value of the function. This is called secure multi-party computation. It is possible to do information theoretically. So you can use this idea in order to implement any proof labeling scheme in a secure way. There's a few catches here. So you can see in the drawing that all the different parties can talk directly to one another. Typically, secure MPC makes this assumption. All the players can talk directly to all the other players. If you want to use these protocols in a general graph, you're going to need to somehow get these point-to-point channels. And how are you going to do that without revealing information to the intermediate nodes? So it turns out actually that you can do it. There are, by the way, known connections already between multi-party computation and zero knowledge. We are not the first to think of this connection by any means. And the drawback here is that secure MPC can be very expensive. In general, the protocols will require communication that grows with the size of the circuits that computes the function F. So if I give you a super complicated F, where the circuit is almost exponentially large, and we know that there are such functions, then the secure MPC protocol that computes it will also be very inefficient. But for NP, we do know that there are polynomial communication secure MPC protocols, so you can use them. The other thing that you can do is just look at your problem and eyeball it and think about it and design a specific solution like we did for 3-coloring. For example, if you want to do spanning tree verification, one of the most useful primitives in this field, you can actually do it pretty efficiently. You can do it in a one-round algorithm, which sends log n bits on every edge and also communicates log n bits with the prover. So essentially, there's no overhead here for spanning tree verification because you would have needed log n bits of communication with the prover anyway. Let me take a look at the chat quickly. Yeah, of course. Okay. I am going to say 2 words about zero knowledge against coalitions. I'm not actually going to describe the solution, but the question here is, can you do anything if the nodes of the network would like to cooperate with one another? So until now, we've been considering nodes as honest but curious, but every node was by itself. The node was essentially also running the simulator by itself. What if I have some number k of nodes that pool together everything they have seen and use that to try to extract more information about the network? For example, go back to our 3-coloring zero knowledge proof. If I have 2 or 3 nodes collaborating, they can compare their colors. They can extract a lot of information out of that. So the nodes are still going to be honest. They're not going to be malicious and kind of lie to the prover to try to extract information, but they will pool everything they have seen and try to extract as much information from that as possible. So here you can actually use secure MPC to get a solution which, again, might not be efficient in the general case, but is efficient for problems in kind of special classes. And I'm not going to say a lot about how this works, just the basic idea is instead of giving to every node the label that the prover was supposed to give it, now I can't afford to do that because this node might share the label with other nodes in its coalition, and then they'll look at all their labels together and maybe learn some interesting things out of that. So I don't want to give any node its label. Instead, I'm going to take this label, I'm going to split it with something called secret sharing between some other nodes in the area. And secret sharing basically means that I'm going to give them these things that look completely uniform. By themselves, they convey no information. But if you look at them all together, you can recover the original label. After I've done that, I am going to need to actually implement the verification procedure, which I'm just going to show you the picture for this. Because I worked hard on this animation, but it is possible, ultimately it is possible to verify whether or not a single node should accept, even if the node doesn't have its label, but rather the label is split between nodes that are immutable. Okay, so let me conclude. I'm gonna pass through this. Yeah, let me just really quickly conclude. What I described to you today was one particular connection between distributed proofs and zero knowledge proofs. And I think that in general, there is a lot that can be done to draw these connections and make them stronger. So proofs in theoretical computer science are kind of a main through line of complexity theory. There's a really rich theory, which is truly beautiful and elegant. And also it turns out, kind of surprisingly maybe, that it's useful for things like cryptocurrency, even for things these days like verifying that financial companies are properly following the rules of the SEC without having them disclose secret business information. Proofs in distributed computing also have a rich theory behind them. They're also beautiful, and they're also useful, for example, in self-stabilization. I think that these 2 areas can actually go really well together, and we should try to connect them more than we have been doing so far. So let me end here, and thank you all for your attention. I know that over Zoom, it's not easy. And if there's any questions, I'm happy to take them.
Thank you very much, Rotem. So for this nice talk, any questions from the audience to Rotem? You don't have much time, but yeah. I guess for 1 or 2 questions.
I have a quick question if there's time.
Yeah, sure.
Do you have any statement of the sort of which problems have a distributed zero knowledge proof? Which languages?
All problems, but you'll have to pay for it, because look at the decision procedure, which takes the labels of the neighbors and the label of the node itself. Think of it as a circuit that just says I accept or I reject. You can verify, you can basically take a compiler that will translate this into a zero knowledge proof. But if this circuit is complicated, then you'll get a zero knowledge proof, which might have exponentially long labels. or exponentially long communication with the prover.
Okay, thanks. Yeah.
Any other question? Is the amount of randomization important in all this? Do you try to optimize it? There was a question from
yeah, this is a really, really great question. We know that randomness is essential. So there are things that you provably cannot do without randomness, but we don't know how much randomness is necessary. This is actually open even for classical secure multi-party computation. This is a really great question, and we don't know.
Interesting. One last short question by anyone to Rotem? If not, thank you very much, Rotem, for this really nice talk. So
thank you, everybody.
Good. So then I think it's already time for the first session. So while maybe Peter, you're setting up the session.
Yeah.
I don't know. It's maybe
just for information. The transcript of the questions and is given by Przemek on Zulip, so you can see the history of questions there.